coloring. What's the official definition we're working with here?
So at its simplest, a graphodaler is just a set of vertices, we can call them V, and a set of edges, E.
Vertices are the things, the tasks. Edges are the conflicts between them.
Perfect. A coloring is just a function. It assigns one of taller labels, which we call colors, to every single vertex.
And the proper part is the key. That's the real-world constraint.
Precisely. A coloring is only proper if any two vertices that are connected by an edge, meaning they conflict, get different colors.
So if color 1 is the Monday 9 a.m. slot and task A and task B conflict, you just can't give them both color 1. One has to be bumped to color 2.
Right. Maybe Tuesday at 9 a.m.
And when we finally boil it all down, when we find that absolute minimum number of colors,
That's the goal.
that satisfies the rule for the whole graph, that's what we call the chromatic number.
Exactly, the chromatic number. Or Phrygia level. It's basically the holy grail of this kind of optimization. Finding it means you've used your resources perfectly. No waste.
Okay, let's ground this with the simplest possible example, a path graph, T $3.1. So that's just 3 vertices in a line.
Yep. $1 is connected to $2, and $2 is connected to $3. That's it.
So if we try to use just 2 colors, say color A and color B, where do we start?
Well, let's just start at one end. Let's give $1 color A.
Okay, so $V is A. Now $2 is connected to it, so it can't be A, it has to be B.
It has to be B. Now we get to $30. It's only connected to $2, which is color B.
Which means it's free to reuse color A. There's no conflict. So the pattern is A, B, A.
And there you have it. We colored the whole thing with just 2 colors. We obviously could do it with 1, so.
So the chromatic number, PD3, is 2.
It's 2. And that simple example sets the stage for everything else we're going to talk about. The entire game is finding that smallest possible number.
Finding that number, though, is, well, it's famously difficult, computationally speaking.
Oh, incredibly hard.
So before we even try to find the perfect coloring, we need to define the absolute basement, the mathematical floor. What's the non-negotiable minimum number of colors a graph's structure demands?
And that brings us to the most intuitive idea, which is all about density. It's dictated by something called the clique number.
We hear the word clique in real life, you know, a tight-knit group. I'm guessing the mathematical definition is similar.
It's very similar. A clique in a graph is a set of vertices where every single vertex in that set is connected to every other vertex in that set.
Okay, so total mutual conflict.
Total mutual conflict. If you think of them as meetings, every meeting in that clique overlaps with every other meeting. There's no way to schedule any 2 of them at the same time.
They're completely interdependent.
Right. And that gives us what's called the clique number. We symbolize it as omega G.
Omega G.
Right. And it's just a number. It's the size, the number of vertices in the largest possible clique you can find anywhere in that graph.
So it's like finding the single biggest, most tangled up group of conflicts in the whole system.
That's a perfect way to put it. And the implication for coloring is it's immediate. It's absolute.
Yeah, if you have a clique of, say, 10 vertices, they all clash with each other.
So they all must get a unique color.
All 10 of them.
Which means the total number of colors you need, the chromatic number, has to be at least as big as the
Let's work
clique
today
number.
to make tomorrow a better
so
day.
greater than or equal to
You
make it.
can do
That's
it.
our most fundamental
Let's
lower
work today
bound.
to
It's
make
the first
tomorrow
place
a
you
better
always look.
day.
Let's take the most
Okay.
dense small graph
You can
possible.
do it.
The
Let's
complete
work.
graph, K4. That's 4 vertices, all connected to each other.
So K4 is, by definition, a clique of size 4.
Right, so its quick number, Femega, K4, is 4.
Yep.
So without doing any other work, we know for a fact that K4 has to be at least 4. And since we can just give each of the 4 vertices its own color.
We know it's exactly 4. In this case, the lower bound gives you the exact answer. The densest part of the graph is the whole graph.
Okay, but hold on. If that's the hard limit, why doesn't the chromatic number just always equal the clique number? I mean, if the clique is the densest part, why would a graph ever need more colors than its biggest clique?
And that is the single most important question in all of graph coloring. It's the reason this is a hard problem.
Okay.
Think about a 5 cycle, a pentagon, C5 times $. Go looking for cliques in there. What's the biggest one you can find?
Just any 2 vertices that are next to each other, a single edge, so a clique of size 2.
That's it. So Timothy color is 2. The theorem tells us we need at least 2 colors.
Right. Taisu5 is greater than or equal to 2.
But try to color it with 2 colors. You go A, B, and then you get to the 5th vertex. It's connected to the 4th one, which is B, and the 1st one, which is A.
So it can't be A and it can't be B. You're stuck.
You're stuck. You need a 3rd color. So here's a graph where the unit G is 3, but the mega G is only 2.
And what causes that gap?
Odd cycles. That five-sided ring structure introduces a global constraint that isn't captured by looking at local density. It's a non-local problem, and that's what makes it so complex.
So the clique number is necessary, but it's not always sufficient.
Exactly. Which means we need to look at the problem from the opposite direction. Instead of focusing on maximum conflict, let's focus on maximum cooperation.
Maximum reuse of colors.
Which brings us to the independent set.
Okay, so if a clique is total conflict, an independent set must be zero conflict.
Precisely. An
No, no.
independent set is a collection of vertices where no two of them are connected by an edge. They are all strangers to each other.
And if there's no conflict within a set, that means every single member of that set can share the exact same color.
They can all be color 1. And we use alpha G for the size of the biggest possible independent set you could find.
So, wait, every color we use in a proper coloring, the set of all vertices that are, say, blue, has to be an independent set.
It has to be, by definition. So what we're really doing when we color a graph is we're breaking up all the vertices, all NG, all of them, into a bunch of independent sets.
And the number of sets we need is the chromatic number.
Right, so that gives us another way to think about a lower bound. If you have NG total items to color, and the biggest possible group that can share one color is size alpha G.
Then the number of colors you need has to be at least the total number of items divided by your most efficient group size.
You got it. The formal bound is greater than or equal to NG divided by alpha G. It's a measure of efficiency. You can't do better than what your largest possible conflict-free team allows.
Let's test that on the 6 cycle. 6C6 sidles, a hexagon.
Okay, so 1G is 6. 6 vertices. In that ring of 6, you can pick every other vertex.
Right, positions 1, 3, and 5. None of them are touching.
So you have an independent set of size 3, and you can't find one of size 4. So alpha G is 3.
Okay, so plugging that into the formula, 2G must be greater than or equal to 6 divided by 3, which is 2.
And we know C6 color 6 it can be two-colored. You just alternate AB, AB, AB. It worked perfectly.
So in that case, both lower bounds gave us the right answer. The clique number was 2, and this independent set bound is also 2.
They both pointed to the same floor. But sometimes they won't. Sometimes a graph won't have any big cliques, but it also won't have any big independent sets.
So you have low local density, but also low potential for reuse.
And that's a recipe for a high chromatic number. The lack of large independent sets forces you to cycle through your colors really quickly, even if there isn't one big hotspot of conflict. You have to satisfy both of these lower bounds at the same time.
Okay, so we've established the theoretical floor, the basement. Now let's go from the basement to the roof. We need practical ways to actually find a coloring.
Right, methods that give us a guaranteed upper bound. A number of colors we know we will absolutely not exceed, even if it's maybe not the best number.
And the simplest, most straightforward way to do that is with the greedy algorithm.
It's the most computationally cheap approach. It requires almost no foresight.
How does it work in practice?
It's completely sequential. You line up your vertices in some order, any order, really, $1, $V, and so on. When you get to a vertex, say $V did, you just look at its neighbors that have already been colored.
The ones that came before it in the line.
Right. And you just assign $, the smallest numbered color that none of those neighbors are using.
Smallest available. It sounds fast. It definitely produces a coloring. But I sense a but coming.
But it's often not a very good coloring. The reason it's important, though, is that because it always works, it gives us a really powerful, if sometimes loose, upper bound. And that bound is related to the graph's maximum degree.
The maximum degree delta jet. That's the vertex with the most connections, the busiest node in the network.
Exactly. So let's think about the worst-case scenario for the greedy algorithm. When you get to that busiest vertex, what could have happened?
Well, all of its neighbors, all delta of them, might have already been colored before it.
And in the absolute worst luck, they might have all been assigned different colors. Color 1, color 2, all the way up to color delta.
So when our busiest vertex finally gets its turn, it looks at its neighbors and sees this rainbow of delta different colors already taken.
So what does it do? It's greedy. It just takes the next available one.
Color delta plus delta.
Color delta plus lot 1. And that right there proves the simplest upper bound theorem. Will always be less than or equal to delta, plus a little. It's a guarantee. You'll never need more colors than that.
It's a reliable guarantee, but it can be, as you said, incredibly pessimistic.
It can be a disaster for efficiency. And this is a huge takeaway for anyone designing a real system. The fastest, simplest algorithm can lead to massive resource waste. Let's use the star graph, K1 to Towers, to see just how bad it can be.
Okay, so a star graph is one central vertex connected out to 4 leaf vertices. And the leaves aren't connected to each other.
Right. So the maximum degree delta G is clearly 4. That's the center vertex.
So our simple bound says we might need up to $4 plus 1 with these five colors.
5 colors. But what's the actual chromatic number?
It's 2. You color the center with color 1, and since none of the leaves conflict with each other, they can all be color 2.
So the greedy approach has the potential to overestimate the resource need by 150%.
Wow.
Think about what that means if this represents bandwidth in a network. That's 150% of wasted capacity, wasted money, wasted infrastructure, all because of a bad algorithm.
So what went wrong? Why did it fail so badly?
It all comes down to the arbitrary ordering. If, by bad luck, you choose to color that central, highly connected vertex last.
Ah, I see. If you color the 4 leaves first, the greedy algorithm might give them color 1, color 2, color 3, and color 4. Then the center vertex comes along and sees 4 different colors, forcing it to take color 5.
Exactly. But if you just colored the center vertex first, it would take color 1. Then all 4 leaves would see their only neighbor has color 1, so they'd all happily take color 2. Optimal solution found instantly.
So the failure is a lack of structural awareness. It doesn't know to prioritize the most constrained parts of the problem first.
Which leads us directly to a smarter approach. We need a better upper bound, one that's aware of the structure, and that's the Welsh-Powell bound.
Okay, so how does Welsh-Powell fix the ordering problem?
It's a simple, elegant fix. It says, don't use an arbitrary order. First, sort all the vertices by their degree, from highest to lowest. Then apply the greedy coloring algorithm.
So you force the algorithm to deal with the busiest, most constrained vertices first.
You do. You make them claim the low-numbered colors early on, which, in theory, leaves more options open for the less connected vertices that come later.
And this gives us a tighter mathematical bound.
A much tighter one. The theorem says less than or equal to 1 plus the maximum value of a specific calculation you do for each vertex.
And that calculation is?
You take the minimum of 2 numbers, dealer, which is the degree of the i's vertex in your sorted list, and II1.
Okay, let's break that down. Deal is the number of neighbors, that makes sense. But II1, where does that come from?
II1 is the number of vertices that have already been colored by the time you get to vertex 11.
Here.
So it represents the absolute maximum number of different colors that could have possibly been used by its predecessors.
I see. So for each vertex, you're looking at 2 potential bottlenecks. One is the actual number of its neighbors, dealer. The other is the size of the color pool, II1, that's already in play.
And you take the minimum of those two because that's the real constraint on the color you're about to pick. It's a much more nuanced view.
Okay, let's try the example. A graph with sorted degrees of 3, 3, 2, 1, 1.
5 vertices. So for IOLED, the first vertex, we have DO1, IO11, which is lending $3. That's 0, 1.
So the bound so far is $1 plus 0 at 1, obviously too low.
For IOA2 is the second vertex, we do M3, $1, 1. That's $1. The bound is now $1 plus 1 day 2.
Okay, for I part 1, 3, 1, it's SEM2, which is 2. The bound becomes $1 plus 2 equals 7, 3.
And if you check the rest, you'll find that 3 is the highest value you get.
So the Walsh-Powell bound tells us we are guaranteed to be able to color this graph with 3 colors.
Exactly. It's a much smarter, more structurally aware estimate than just looking at the maximum degree of 3 and saying we might need 4 colors. It pays to be smart about your ordering.
So now let's shift gears a bit. We've talked about general bounds, but what about specific types of graphs? Sometimes the underlying structure of the problem makes coloring much, much easier.
Right. If you know the specific nature of your system, you can often use a shortcut.
Let's start with combining systems. What happens when you take 2 graphs, Dillon and Ullers, and merge them using what's called a Cartesian product?
Jewel-Cox H.
This often looks like a grid. You can think of the vertices of the new graph as pairs, with one component from dollars and one from dollars. So if dollar represents conflicts along, say, a vertical axis, and a dollar represents conflicts along a horizontal axis, the product graph is the full grid of conflicts.
Right. And what's really beautiful here is how the coloring complexity works out. It's incredibly simple. The theorem just says that the chromatic number of the combined graph, Y-box H, is simply the maximum of the 2 individual chromatic numbers.
So dolly makes H.
That's it.
That's amazing. So the less complex system adds 0 additional coloring complexity. The whole new system is only as hard to color as its hardest component part.
Exactly. The total resource need is dictated entirely by the more demanding of the 2 original systems. So if you take our path T33 tall, which needs 2 colors, and our 5-cycle C5-5s, which needs 3.
The Cartesian product of the two, 3p3-doxy-5-vialer, will need Bax 2, which is 3 colors. The 5 cycles complexity just dominates.
It's a really powerful result for any kind of system built on orthogonal or independent dimensions.
Okay, now for a class of graphs that is hugely important for anyone doing scheduling, interval graphs.
Yes. This is where the abstraction of graph theory meets the very concrete reality of a timeline. In an interval graph, each vertex represents an interval of time, a meeting, a task, a machine operation.
And an edge exists between two vertices if their time intervals overlap.
The quintessential scheduling problem.
Yeah.
Now, what's so special about these graphs is that the thing that made coloring hard for general graphs, those weird odd cycles, just can't happen here.
Why not?
Because time only moves in one direction. The linear nature of the timeline prevents those complex non-local looping constraints from forming.
And that structural limitation makes coloring easier.
Dramatically easier. For any interval graph, the difficult gap we talked about earlier disappears. The chromatic number is exactly equal to the Clink number.
Wow. So for scheduling problems, the minimum number of resources you need is determined purely by the single point in time with the most simultaneous overlapping events.
That's it. The point of maximum density is the only thing you need to worry about.
So what does that mean for actually finding the coloring? Do we still need complex algorithms?
Not at all. The optimal strategy becomes incredibly simple. You just sort all the intervals by their start times.
Their left endpoints.
Their left endpoints.
Yeah.
And then you just apply the simple, naive, greedy algorithm. And because of the special structure of interval graphs, that simple process is guaranteed to give you the perfect optimal coloring every single time.
That feels like the holy grail of system analysis, finding a hidden property of your system that turns an NP-hard problem into a simple sorting problem.
It is. Let's run the quick example. 4 intervals. A, B, and C all overlap, forming a clique of size 3. D starts after all of them are finished.
Just a clique number, omega G is 3. We know the answer should be 3.
Okay, sort by start time. A, then B, then C, then D. Greedy algorithm time. A gets color 1. B overlaps A, so it gets color 2. C overlaps both A and B, so it has to take color 3.
Now D comes along. By the time it starts, A, B, and C are all finished, so the colors 1, 2, and 3 are all available again.
And since it's greedy, it takes the smallest one available. Color 1.
Total colors used, 3, which is exactly to omega G. The simple method found the perfect solution.
Let's turn now to the absolute building blocks of color complexity. The things that force a graph to need a certain number of colors. We call these K-critical graphs.
They sound like irreducible pressure points.
That's a great way to think of it. A graph is called K-critical if its chromatic number is $2, but, and this is the key part, if you remove any single vertex, just one, the chromatic number of what's left drops to K dollar colors.
So they're perfectly balanced on the edge of needing K colors. Every single piece of the structure is essential to that requirement.
Exactly. If you find a 4-critical subgraph inside your giant, messy system, you know with absolute certainty that you need at least 4 colors. And you also know that to get that number down to 3, you must break that specific subgraph apart somehow.
It's like a load-bearing wall for color complexity.
It is. And these critical graphs have a very specific mathematical property. If a graph is K-critical, then the minimum degree of any vertex in it, we call that delta, or HL, has to be at least K null or 1.
You can do
So
it.
every node has
Let's
to be
work
pretty
today
well
to
connected.
make
It can't have any
tomorrow a
loose
better
ends.
day.
Right. If
Okay.
a vertex had too few neighbors,
You can
it
do
wouldn't
it.
be constrained
Let's
enough to
work
be truly
today to make
critical in
tomorrow
forcing
a
that
better
K color.
day.
Let's check that with our old friend, the 5-cycle
You can do it.
CC5. We
Let's
said it was
work.
3 critical.
Yes, C533, and if you remove any vertex, you're left with a path which is 2 colorable, so it fits the definition.
Okay, so here, fee $33, the property says the minimum degree must be at least K null or 1, which is 2.
And in a 5-cycle, what's the degree of every vertex?
Every vertex has exactly 2 neighbors, so the minimum degree is 2.
It holds perfectly. They're these perfectly efficient structures of conflict.
Okay, we've covered the fundamental structures.
Yeah.
Let's move into some even more advanced theorems that give us tighter bounds by looking at, well, not just the single busiest vertex, but the density of the most challenging internal teams or subsystems.
This is where the Sekker's Will theorem comes in. It's a much more sophisticated way to get an upper bound than just looking at the global maximum degree.
So how does it capture this idea of local bottlenecks?
The theorem states that it's a less than or equal to 1 plus the maximum minimum degree found in any subgraph of G.
Okay, say that again. The maximum of the minimums.
The maximum of the minimums. It's a bit of a mouthful. What it's telling a system analyst is Don't just look at the single most connected person in your whole company. I want you to go and look at every possible team and sub-team.
Okay.
And for each of those sub-teams, find the person with the fewest connections within that team. That's the minimum degree, delta. Then, I want the highest one of those values you found across all possible sub-teams.
So you're hunting for the most tightly knit, resilient pocket of the graph, a group where even the least connected member is still really, really connected to the rest of that group.
Precisely. That densely interconnected core is what really drives the need for colors, even if the graph as a whole looks pretty sparse. The practical way to find this is often to peel the graph.
You peel it.
Yeah, you find the vertex with the current minimum degree, and you remove it, and you keep track of what that minimum degree was. Then you look at the new, smaller graph and do it again. As you peel away the loose outer layers, you might suddenly see the minimum degree jump way up. That's you finding the dense core.
Let's try that on a 4-cycle with a diagonal. So 4 vertices, and it
Okay.
looks like a square with one line through the middle.
Okay, so the degrees are 3, 3, 2, 2. The minimum degree is 2. So we note that down and remove one of the degree 2 vertices.
What's left is a triangle with a tail, or a K33 with an edge hanging off. The degrees are now 2, 2, 1. The minimum degree is 1.
We peel off that degree 1 vertex. Now we just have a K33 or the degrees are 2, 2, 2. The minimum is 2.
And so on. So the sequence of minimum degrees we observed during the peeling was 2, then 1, then 2. The maximum of those is 2.
So the Sekres-Wilf bound is $1 plus 2 equals 3 or 3. And that graph is, in fact, 3 colorable. The simple bound would have said $1 plus delta, which is $1 plus 3, equals 4 2-gar. So this method got us a much tighter, better answer.
That's incredibly powerful. Now, for what you called the most mind-bending connection of all.
The Galois-Vitaver theorem.
Mm-hmm.
Yeah, this one completely reframes the problem. It shifts from thinking about static labels colors to thinking about dynamic flow.
So how do we get from coloring to flow?
First, we have to take our graph d'Array, and for every edge, we have to pick a direction. We turn it into a directed graph or an orientation d'Array.
So for every conflict, we're imposing a dependency. A must happen before B.
You're creating a workflow, a sequence. The theorem then asks you to find the length of the longest directed path in that orientation you just created.
A directed path being a sequence of vertices where you're always following the arrows.
Right, and here's the theorem. The chromatic number is always less than or equal to 1, plus the length of that longest path.
Wow. So the number of resources we need is directly tied to the longest chain of sequential dependencies we can create in the system.
That's the profound insight. Coloring is equivalent to finding the most efficient way to serialize all the conflicts. If you can arrange the dependencies such that your longest chain is only, say, length 4, you're guaranteed to need, at most, 5 colors.
But it gets even better than that, right?
It gets much better. The kicker is, while that inequality holds for any random orientation you pick, the theorem also guarantees that there exists at least one special, optimal orientation where equality holds, where it's exactly $1 plus LESD.
So if you can find the orientation that makes the longest path as short as possible,
You have found the chromatic number. You've solved the problem.
you've turned the coloring problem into a pathfinding problem.
Let's go back to the triangle. Take you $3. We know it needs 3 colors.
Right.
Let's orient the edges. Let's try to make a path. V mu dol to V2 to V32. We can't go any further because the next edge has to go from V through $3 back to V$1, which would complete a cycle, not extend the path.
So the longest directed path you can make is length 2.
The longest path is 2. The theorem says less than or equal to $1 plus 2, which is 3. And since we know the answer is 3, we found one of those orientations where equality holds.
The need for 3 colors is a direct result of the fact that you can't orient a triangle without creating a dependency chain of length at least 2.
Exactly. Now, what about our simple path, 3p $3? We know p $3.
We know to par dollars does a straight line, $V to V2 to V33. The longest path is length 2.
So the bound says lec 1 plus 2 equals $3 run. That's true, but it's loose. The theorem promises us a better orientation.
An orientation where the longest path is only length 1.
There has to be. And we can actually use the optimal coloring to find it. Remember, the coloring was 1, 2, 1.
For $V, V2, V333.
Let's create an orientation by having every edge point from the higher colored vertex to the lower colored one. So the edge between $V color 1 and $2 color 2 must point from V2 to $V.
Okay, $V to V.
And the edge between $2 and $2 color 1 must point from V to V3.
So we have V left arrow, V2, right arrow, V33. What's the longest path in that orientation?
It's just length 1. Either $2 to V or V to V3. You can't chain them together. So like D,
And $1 plus LD is $1 plus 122.
which is the exact chromatic number. Equality holds. It's just a beautiful, beautiful theorem. The search for colors is the search for the shortest possible dependency chain.
This has been just a phenomenal journey through the logic of resource allocation. We started with the absolute basics, proper coloring, the chromatic number, and then established those hard theoretical floors.
Right, the limits imposed by density with the clique number, the mega G,
Mhm.
and the limits on efficiency with the independent set ratio.
We then got into the practical side, seeing how a simple, naive, greedy algorithm can be so wasteful, like with the star graph, but how a little bit of structural awareness, like sorting by degree for the Welsh-Powell bound, makes a huge difference.
And we saw that knowing your graph structure is everything. If you're on a timeline with an interval graph, the problem just, it melts away. It becomes negative.
And we identified those core bottlenecks, the critical graphs, that you have to find and break if you ever want to reduce your resource needs.
And finally, we move to those advanced bounds. Sekker's Wilf, which links the global color count to the densest local subsystem, and of course, Galois-Vitiver, which just completely transformed the problem into one of optimizing flow and dependency.
It really does take something that feels chaotic, all these conflicts, and turns it into this elegant, bounded mathematical puzzle.
And that, I think, leads us to the final, really critical thought for you, the listener, to take away. We've said a few times that finding the exact chromatic number is NP hard.
Meaning, for any large, complex system, it's basically computationally impossible to find the perfect answer in a reasonable amount of time.
Right. And because it's so expensive to find that optimal solution, what do you think most real-world systems do? They don't even try. They run a quick, easy algorithm, like the greedy one.
They settle for an upper bound, a solution that is guaranteed to work but is almost certainly not optimal.
Exactly. So here's the provocation. Think about some massive critical system you rely on. A university timetable with thousands of classes, a national logistics network, a cellular frequency plan for a whole city.
Okay.
That system is probably operating with, say, 5 colors, 5 sets of resources. It works. But given the huge gap we've seen between the easy upper bounds and the true hard lower bounds, it is incredibly likely that the actual mathematical non-negotiable minimum number of colors it needs is only 3.
And the only reason it's using 5 instead of 3 is because finding that 3 coloring is just too computationally hard to be worth it.
So the deep dive challenge for any real-world optimizer is this. Is the cost of the wasted resources, those 2 extra colors, more or less than the immense computational cost of proving you could do without them? That is the hidden, constant trade-off between guaranteed function and perfect efficiency.